1 and maybe a 2 or a 0.5, this would be valid.
Whoa.
But there are certain conditions that it must have. For example, for all booleans in B, for all numbers in B, p plus 1, and also you define the operators plus and times, which are or and, right? So you define what these are. So they need to have some of the same behaviors as booleans do. These are the domination laws. It says p and 0 equals 0 for all booleans. P plus 1 equals 1 for all booleans, right?
Yeah.
Does that make sense? Or true equals true. And false equals false. Then there's also the complement rules. So p times the complement of p, you also define what a complement is.
So that's always false, right?
This is always false. And then p plus the complement of p is always true.
Hey, I know these rules. They're from the comp side.
They also need to be associative. You guys know what that is from algebra? So that means A, B,
Oh,
C
wait, Kevin,
equals
you have food, please,
A times B, C.
What? You have an instrument of food.
Okay, guys. So hold on, Kevin. I'll catch you guys up. A Boolean algebra is a set that contains 0 and 1. You know fuzzy logic?
Fuzzy dice.
Okay.
No, not fuzzy dice.
You know fuzzy logic, right?
Kind of.
Okay, so
Furry logic.
stop. This is going in the recording. Okay.
Why is everyone so small? I just died.
Stop. Okay, so fuzzy logic is one example because it's like you can have a continuous range of booleans. So like 0.333 is a boolean, and 1 over e is also a boolean, and like you know Euler's number, like literally any number between 0 and 1 is a boolean. And there's this language for how you I don't know. But it behaves, but the thing is, for zeros and ones, it has to behave just like normal.
Wait, you can have numbers between 0 and 1?
Yes, that's
For
like
fuzzy logic, that is one Boolean algebra.
It's like
This
kind
is
of like a Boolean,
so-
but not really a Boolean.
So a Boolean algebra, in a Boolean algebra,
Boolean
you can add extra numbers and you can make the operations work weird for them. But for 1 and 0, they have to work just as normal. They need to have these domination laws. So p or true equals true, p and false equals false, p or not p equals false, p and not p equals false, p or not p equals true. Those are true for normal Booleans, so these things have to be true of all Boolean algebras, but you can extend it. Like, you know how you extend the natural numbers into the rational numbers? And the rationals share all of the same properties as the natural. What?
Oh, no, he's talking.
No.
What was
I
it?
was talking about Boolean algebra, obviously. And how it extends into our daily lives.
Okay, well here's the thing. So, you extend natural numbers into rational numbers, right?
Hey, get a little to the right. You're not.
What? It's not like I'm saying you expand or something.
What?
You
Yeah,
can-
you bit to the right. Yeah, that's better. No, that's too far.
Hey, can you not
Don't stand in front of the stuff.
overshadow all my talking?
Dude, why don't we
and
just
laughing?
like move
Eli,
this?
move that. No.
See, yeah, see.
No, because then it starts wiggling around.
No, it won't.
Go this way.
Oh
Okay,
my
this
God.
time.
Just leave it be. It'll be fine. Okay, so
Okay, that's actually.
it also needs to be associative. That means A times B times C equals A times B times C. And also the same thing for A plus B, right? Plus B plus C. Yeah, whatever. You get the point. It needs to be commutative, which means that it works both ways. Matrix multiplication is not commutative. That means that AB equals BA. A plus B equals B plus A. Right? And it needs to be distributive. I assume you guys remember what that means, right?
Totally.
What's distributed?
It means communism.
Okay, so A times A times C plus D. Stop. So A times C plus D is AC plus AD. These all mirror properties that normal numbers have.
80.
These all mirror properties that Booleans have. So a Boolean algebra needs to have both of these be true. So I'm going to talk about
Hey,
one.
what's that dash thingy?
That's the
What dash? That's complement. That goes over.
It's like
like you would-
complement.
It's like not.
Oh, it's not. Oh, okay.
Yeah.
This back.
Oh,
I know stuff.
All right. So guys, can I erase this?
David, that's
I'm going
my
to show you an
personal
example of a
property.
Boolean algebra, and I'm totally going to
Boolean
screw this up
algebra.
because I was like thinking about this a couple minutes ago, and I was like, wow, fuzzy logic would be a great example to
Fuzzy
teach this.
dice.
I'm pretty sure fuzzy
Fuzzy
logic is a
logic.
Boolean algebra. Not, I'm like 90% sure. Okay, so our set is going to be b equals 0, 1. But I didn't use the set brackets. You know why?
Because it's the main vector.
Because it's not a
No,
set.
it's not a vector. It is a range.
it's
This is a
an
closed
array.
range, dude. No,
Oh.
it's not an array.
That's what we learned
This
from
is a closed
algebra
range.
too.
It's all numbers on the number line from 0 to 1.
Wait, oh, that's the interval notation.
Oh.
Okay, and so what we're going to say is that P plus Q is the maximum of P and Q. Does that make sense? Why? Because for Booleans, when you say P or Q, right,
Oh, I see.
you just choose the bigger one, right?
Oh, yeah.
So if it's true,
Hmm.
like if you know that something is more true than the other is, this is supposed to
More
say like
true.
this is for partial truths. This is
Oh.
fuzzy logic. So if something is more true than the other, so if you want to say like, for example, like
Obama.
let's
is
say there's
born
a
in
there's a very
America
small no.
Is 0.
Okay, I didn't even hear what you said, but
Eli is correct. 0.
in case we ever publish this, let's not talk about like politics stuff.
Oh.
Oh yeah, good point.
Why would this be called?
Dude, like, why do you think I kept the sombrero out of the
0.9.
video?
1-0.
A couple of meetings ago. Anyways,
How do I play a sound on my MacBook?
no, do not play a sound on your MacBook.
I'm holding on to his
I'm
MacBook for the
afraid
duration
to
of
hear
your
what that
meeting.
sound might be. Okay,
Where's
so
I have my slide.
so let's say you have somebody's like okay, like somebody says that
We almost went down the politics road.
yeah, so somebody says that stats is more important than calculus, and that is a 70% truth value, right? So that's 0.7, right?
Mm-hmm.
And so
Only
then
a
somebody
partial
else
truth.
says that the aliens took me and put me back when I was 5 years old. That is
so
going to have
wide.
a truth value of 0.05. We're going to take the larger one, right?
Yeah.
If we say either the aliens took me, or the truth value of the aliens took me, or stats is more important than calculus, we're just going to take the larger one,
Wait,
right?
So, stats being more important than calculus is only 14 times more true than being adopted by aliens.
Yes. Yes. That is.
Oh, my Mac will only play a sound when it's connected to the internet.
Dude,
David, can you
that's
connect
not
it
even
to
a
the
Mac.
internet?
Hit up my hotspot.
I have his
Oh,
Mac. I'm
wait,
holding on
get
to
my
his
Dude, literally turn off
I'm
your.
holding on to his Mac for
Okay,
the
hotspot's
meeting.
on.
Okay, good. Okay, so
Oh, your hotspot's on.
and another rule, guys. PQ is the min of P and Q. So if I said that thing about the aliens, so I was abducted by aliens, and also this doesn't exactly mirror actual statistical rules that you learned in stats. Just like totally ignore that part, please. The fact that this is actually like super wrong. Anyways, this is what they do in a bunch of like algorithms. So just like think about it this way. It's convenient.
Lance
So if you said the same examples of
Okay, and so we're gonna say like the probability that the aliens abducted me, and or no, not the probability, the truth value that the aliens abducted me and calculus is more important than stats is whatever the lesser of them is.
So it's not just false?
Well, no, it would be the minimum of the two, right? So you see why if you did like 0, 0, it would be 0, right? And if you did 0, 1, that would be 0. If you did 1, 1, that would be 1, right? You get why this has all the same properties as Boolean logic. And I would check the conditions I just said, but that would take forever. Anyways, so this is an example of a Boolean algebra. Wait, I didn't say what the complement is. Okay, so the complement is 1 minus P. Does that make sense, why?
Good afternoon, everybody. Can we please get our cars moved from the Shaq Court Stadium to
No.
as soon as
Oh, gotta go,
possible?
guys.
Thank you so much.
But you're not.
Wait, I have my car's outside. Can I have my MacBook back while I go get it?
You're not even old enough to draw.
Okay, guys, so the truth value of not p is 1 minus the truth value of p. You get why that is,
Oh,
right?
yeah.
So 0 turns into 1, 1 turns into 0, 0.3
Eli,
turns
I have
into
a question.
0.7 or something.
Wow, these
Eli,
90
I have a
I don't know.
question.
So this is
How
our new
much?
Boolean. This is the fuzzy
How
logic
much?
Boolean algebra, and I believe it needs.
Can we move on to furry logic?
Yeah, that's my favorite logic.
Eli,
David,
I have
give me
a
my
question.
MacBook back.
I have a
Guys,
question.
if you invent that, it's
I have
like
a
it's actually.
question.
Guys, you should invent
I have
something
a
called that, and I'll
question.
actually teach about it.
Okay, let's start with the first principle. All animals are flesh, not food. Unless you eat.
Wait.
What
Okay.
kind of friend?
Okay.
Wait, that's
So,
not
what-
the logic.
Who had a real question before
Well, I
Neo
have
started?
a question.
Just-
Why is P times Q equal to min of P and Q?
It's like
Well,
You're basically
Well, this is
mimicking
and.
one
This
times
is
the
P
zero
and Q.
and zero.
So like, let's say this is 0.3 truth value, this is 0.6 truth value. You take the minimum with them.
Oh, okay.
So like, isn't that what you do when you're calculating and? You take the
Yeah.
smallest of the two booleans. Like that's how I think of it, right?
Yeah.
So if it's 1, 1, then I
It
do
is,
1.
right? Because if
It's
you have
1,
1,
0.
1, then you take 1,
Okay,
1,
I
0,
was
you take
thinking
0.
about 0.7
Yeah.
times 0.05.
So this is pretty much this, just generalized onto the continuum between 0 and 1.
Okay.
And so this is a Boolean algebra, and it is called Fuzzian logic.
You mean Furrian logic?
Okay,
Let's
moving
go
on.
make Furrian logic.
Moving on. Okay, I'm gonna go over that circuit.
Yeah.
You guys remember that, the half adder? So I'm gonna add these two numbers, right? X and Y. They're just
Okay.
Booleans, right? Normal Booleans.
Yep.
So I want to, so I'm gonna find what is their sum, like the small digit, right? What is the small digit? How do I find that?
I'll use a and or I don't know. You like there's like
What is
I like the
Dude,
full
it's
adder
X.
more than the half adder.
It's
I feel
X.
like it's more
Wait a second. I think it's.
XOR, yes.
Yeah, it's
exclusive
XOR. Yeah.
OR.
That's-
So this is
I was gonna say that, but I was like, wait a second. Is it X
Okay,
and OR?
so-
Wait, oh, that's what the X
Wait,
and
Eli,
X
this
over
is
Yeah.
stands for.
exclusive.
That's an and. Oh, Eli, bro, this doesn't.
No, dude, you're.
No, this is.
No, wait.
Oh,
Dude,
wow.
look.
I
A,
need
it's
to wash
curved.
this
B,
off
there's
in the
two
bathroom.
lines, so it has to be. It has to be XOR.
So X and Y is.
Okay, and then I'm gonna like take these down, and how do I find the carry?
You do another one.
No.
Oh,
I check if they're. When is it going to overflow?
When it's 1 and 1.
If they are both true. So and. This is our carry, right? So this is a half adder. And another way. Okay, another way I can notate this is just drawing a box and saying half in it. And all the scientists will know what you're talking about,
Yep.
right? Our top one is sum, our bottom one is carry.
I'm
So
a
now-
scientist.
In the next step,
Yep.
okay, so let's say we're adding a number, right?
Yep.
So we have 0, 1, right? 1, 0, 1, 1, 0, 1. Well, anyways, something like this, right? We're adding them, right?
Yeah.
And we're not adding them as an or, we're actually adding them. So we're gonna get 1, right? And we're gonna get a carry of 0, but now we have to add 3 numbers for this step. So now we need to make what's called a full adder.
Whoa, that's two half
In the
adders.
full adder, well, I mean, it uses 2 half adders, but all it
Yeah,
is it's
see?
a carry. It just adds 3 numbers, and one of them is the carry from the previous time. So we're going to notate them carry, x, and y. So what we're going to do is first we're going to add carry and x, right? We're going to add them, right?
Just name all 3 of them X, X, X.
Okay. Or well,
So don't
first
do that
maybe this will make more sense. So we're going to add x and y, right? And then we're going to get the small digit from that, and then we're going to add that and c, right? So this is the sum, right? And then this is the actual final sum we get, right?
What if
We
there's
just-
a carry?
We just sum all 3 numbers, but the thing is, it can only overflow once, right? Because the maximum value is 1, 1, right? 3. If all of these are on, then we're going to get 1, 1. So it can only overflow once. So we're going to see if on either of these additions it overflowed, because it will only overflow on once, then we carry. And the thing is, we can also say, XOR, because it won't be both. It literally cannot be both. So it really doesn't matter if you put an or
That's
an
quitter
XOR right
talk.
there. What?
That's quitter talk.
Okay, well anyways, so does that make sense?
Quitters never win.
So here's the thing, you can call this
Winners
C,
never quit.
we're gonna introduce a new notation for this called CXY, and then you do this, and it's a full. And then some
Winner not
carry,
quit.
right? Make sense? All right. Now I'm gonna draw out how to add the whole thing. So I'm just gonna say x of 0, x of 1, x of 2, x of 3, and these are all of the digits that we're adding, right? Up till the most significant. So we're gonna add these two, right? Half. And the sum, that's our lowest digit, right? That's the sum sub 0. And then the carry goes on to this round, and we do a full, right? Oh wait, I'm dumb. It's x sub 1, y sub, so x sub 0, y sub 0, right? X sub 1, y sub 1. X sub 2, y sub 2, right?
So what if they're
So
like
we're adding two different numbers,
Eli.
x and y.
Eli? What if the first number is longer than the second number?
Yay.
Well, I mean, you can just fill in zeros, dude.
That's a good point.
Okay, and so so what we're gonna do is we take the carry, right? And then we add that in the next step using the full adder, and then we get this part, s sub 1, right? And then we get a carry from this, right? So then we put this into another full adder, and you can see where this is going. We just keep doing this, s sub 2.
Is this how
C sub 2.
calculators are made?
And so then the thing is, this carry, this is actually like the largest digit we have. We're not actually adding this to anything else. So we are just going to label this s sub 3, even though it is the carry from this step. S sub 3 equals c sub 2. And I'm going to say c sub 0, c sub 1. Right? Does that make sense? Okay, so we actually went over that last time. It's just that I didn't understand it myself. Well, I mean, I did, but I totally forgot all of it. I was a bit confused. Anyways, so I explained it really, really poorly.
Okay, cool.
All right,
Wait,
so
are you gonna post last week's video in like the Discord or classroom or whatever?
I don't think we have a complete video.
Can you post some food in our classroom?
Okay, well, anyways, so here's what a Boolean literal is. I just went over the half adder and full adder stuff and how to make a complete adder circuit.
Okay.
That's all you missed. Sorry.
It's not
Is your
so wrong.
shirt good?
Yeah.
Wait, why do you even need?
Well, I went to watch like the marker mark.
Oh, you marked him. Oh, I didn't see that.
What marker mark?
I was assaulted.
Are you watching Minecraft videos?
Yes.
No, don't,
No.
Joseph, don't draw attention. Everybody's going to be watching them instead of me.
Oh,
I
I
got
got
it.
it.
I can vouch.
Don't
But
look at
David
him.
took my back.
You don't look at him. No.
Joseph, you're too
Okay,
skinny to
so
block
a
out.
literal is a Boolean value. Oh wait, I forgot to erase this part. Okay, I'm erasing this with my hand. So a literal is a Boolean value, like it's a Boolean variable. Can you stop doing that? Or its complement. So it's p bar x sub 3 x sub 3 bar, something like that, right? That is a literal. You know what is not a literal? X sub 2 plus x sub 3 or something like that. That is not a literal. That is, yeah. So here's the thing. So let's say we have variables, right? We're going to say we have variables. There's only 3 variables, right? X sub 1, x sub 2, x sub 3. A midterm is one literal for each, is an expression that's a bunch of things multiplied together, right?
Yeah.
But it's one for each variable. So this might be a midterm. A midterm, not a midterm.
A mentor?
Yes, it's a midterm, as in the exam.
Uh,
No, it's midterm.
man, this
M-I-N.
guy's so good at fortune.
Midterm.
Oh,
Okay.
good. I thought it was a man.
Feels so fast. Crazy, this guy's speed.
Okay. Well, anyway, so this is a midterm, right? Makes sense?
Yeah.
Oh,
Midterm.
this guy's faster than Mac.
Okay, so then disjunctive normal form
Awesome. It is covered.
is a sum of minterms. So x sub 1, x sub 2, x sub 3, and then you might say plus x sub 1, x sub 2, x sub 3, or something like that. So literally each of these, so one thing to note, what is special about a minterm? How many possible sets of values for these variables satisfy a minterm?
What's a minterm?
It's like
It's like a mentor.
A minterm is a product of all of one literal for each variable.
What's a literal?
A literal is a Boolean variable, just like x sub 1, x sub 2, x sub 3.
Oh.
You can't have plus or and or anything in that. You can only have complements. So this is a literal, this is a literal, this is a literal. This thing is a minterm. So it's one for each, one literal, all multiplied together, one for each variable. Okay. So what is special about the minterm? How many possible values for these variables? How many possible sets of values for these variables satisfy the minterm? How many is this minterm true for?
Only one.
Only one, yeah.
One that's right.
For this, x1 must be true, x2 must be false, x3 must be true.
Yeah.
For this one, x1 must be true, x2 must be false, x3 must be true. And
Oh,
for this
two
minterm,
possible
x sub
numbers.
1 must be false, x sub 2 must be true, x sub 3 must be
What
true.
does DNF stand for?
DNF is disjunctive, as in disjunction is or. So it is disjunctive normal form. So this is a sum of minterms. Minterms, there's only
normal form
one
is different
possible
from-
set of values for the variables that satisfy each minterm. So this is pretty much saying this has to be the set of, this pretty much corresponds to a set of values, right? This has to be the set of values. And so DNF says either this is the set of values or this is the set of values. It lists all possibilities out that satisfy the equation. It's like really simple and convenient because
always
you
true.
can easily tell all the solutions. Each of these pretty much is a solution. Each of the minterms is one solution. So to convert an expression to DNF, like let's say if it was, let's say you have variables like P, Q, R, right? Q, R are your variables, right? Those are your vars, right? And you have the expression P if P then R, right? How am I going to convert this to DNF? So first thing, I'm going to get rid of whatever the heck this is. This is, does anybody remember what this is?
I can't
Implies.
see.
Implication.
Oh, if then.
Yeah, it's implication. So what we can say that either R is true or P is not true.
Mm-hmm.
And the thing is, well, actually, I'm going to say PQRZ, right? So I'm going to say Z is true and this is true. So then this is true and Z is true, right?
Mm-hmm.
So then you have to, like, now we have an actual expression, right?
Wait, what about Q? Don't you need Q?
Don't I need Q?
No,
well, there's
you
no
don't.
Q in this expression.
Yeah,
do
so
you
to
have
turn
to-
it into like,
Wait,
you
why
have
do
to
you
have
have
one
to
of
see-
each
You need
literal.
to have, that's exactly right. So,
Wait.
but that comes later. So first of all, I'm just going to get rid of this parentheses, right? I'm going to
Yeah.
expand it using distributive. So I'm going to say RZ or complement PZ. You get why that is? Yeah.
Because you add like a Q in front of each of those.
So then I'm going to say next thing's next. Then I add identities for, like, I add identities. You guys remember the identity laws, right?
Yeah.
So I can say R, so I said PQRZ, right? So I'm going to say 1 RZ, because you get, that's the dominate, that's like,
It doesn't.
that's a law. When you say 1 and this, true and this, it's
Yeah.
just the thing that's on the right. Yeah, and so then here, it's P bar 1 Z, right? So then what I'm going to say is that this is P or not P, then this is Q or not Q times R times Z plus not P times, oh wait, and these are ones, times Q or not Q times R or not R. But you guys get how to expand this using distributive, right? Because this looks like a whole pain to distribute.
Yeah.
I don't really want to do that, so I'm just not going to. Okay, yeah, so you would expand this using distributive, and then you keep adding in the variables, expanding using distributive. Get rid of these things if you see any of these weird things that aren't and and
Wait,
or.
so you can get squared values?
Squared?
Yeah.
Well, the thing is, here are the squares stated. 0 and 0 is 0.
That's a good
1
point.
and 1 is 1. Those are your squares.
So could you like just simplify those down to like their just one variable? So like if you said p squared, could you just simplify that down to p? Or
Yeah.
like not p squared, you could simplify that down to not p, right?
Yeah. But the thing is, you won't get that here, I don't think. But anyways, yeah, but
like,
P and P is P. P or P is P. That's like a law or something.
It's a postulate.
No, I think it's a law.
We're going to do proofs.
Wait, P and P is what?
P.
So p and
Dude, what
p
is
is p.
Yeah.
Joseph, what do you think?
1 is 1, 0 and 0 is 0.
Yeah, so P and P is P.
P is not always.
No,
Stop.
P is always 0.
Yeah.
You just ban you.
I'm gonna kick you out. Literally.
Don't kick me.
Neo, if you're going to not contribute anything to the club, be a distraction, and not pay attention, we wouldn't want you in this club.
And so the thing is, guys,
No, but like. can you
stop
tap-
entertaining him. Okay. So max terms, so min terms are just like a product of all of the of one literal for each variable. What is a max term?
Add
You add them all together.
Yeah.
So
Yeah,
it's
so you would say x of 1 or not x of 2 or x of 3, for example. And so what's special about max terms? How many solutions does this have?
1. Oh, no, all. Whoa.
No, all but 1.
All
So
but
5.
one.
If there's something such that x1 is false and x of 2
-1
is true and x of 3 is false, because what this is this is using De Morgan's law. Remember De Morgan's law?
Yeah.
It's like,
Yeah.
okay, so this is essentially
What is De Morgan?
not this.
What is De Morgan?
So look, this is a max term is not of a min term, right?
Oh.
So the thing is, it's everything but this one solution solves it. So pretty much this just eliminates one solution. So for conjunctive normal form, pretty much you say max term, right? Max term. So that eliminates one solution, right? And then times another max term. And then you do this for everything that's not a solution.
Hey, what is the 3
There's
equals
one of
sign?
these for each of them that's not a, for every possible thing that's not a solution. Every possible
What?
set of variables, set of values for the variables that's not a solution.
It's equal to.
Except for the min terms in DNF, you add them all together, and so you say either it's this solution or it's this solution or it's this solution. For
For max
conjunctive
terms,
normal form, you say it's
Let's see.
you say it's not. For conjunctive normal form, you say it's not this non-solution, and it's not this non-solution, and it's not this non-solution, and it's not this
So
non-solution.
CNF must be really long for
So
this one.
it's literally the exact opposite.
Oh.
And so conjunctive, remember? Okay, Joseph, what did I say disjunctive was?
Not add.
What?
No, I said disjunctive was or. Conjunctive is and.
Oh.
Conjunction.
So this is
function.
and normal
What's your
form. You're
function?
anding a bunch of things, max terms together.
Oh, okay.
Okay, so you guys get the principle, how they're like polar opposites? Well, anyways, everybody likes DNF. I don't know why. I think it's better.
Do not fact.
Because people don't like thinking about what's not a solution. People like thinking about what is a solution. They don't like saying it's this or this or this. Not saying it's not this, and it's not this, and it's not this.
Yeah.
That's the difference. Okay. Alright, I got done with that. Got done with the circuits thing. Alright, Karnaugh Maps. Alright.
Who's Karnaugh? Isn't that guy from Harry Potter?
Karkaroff.
Karkaroff.
Okay, so a Karnaugh map is a big rectangle.
What the hell?
Guys, a Karnaugh map is a big rectangle. This is important. And
I
so,
like rectangles.
The Earth is a rectangle.
Rectangles are just crappy squares.
No, they're just elongated.
Squares are just overachieving.
okay, so guys,
rectangles.
do you notice anything about like these things that I'm putting on the side of the square, right?
Yep.
Oh, they're all the possibilities.
These are all ands.
They're
So
all
it's not a
possibilities.
rectangle. Did
But
you
what
divide
about the
them?
ones that are next to each other?
What?
Oh, they're P and Q.
What? Yeah, well, yeah, that's true. All of them are on this side are regarding the same variables. All of them on that side are the same variables. But what's true about these is that you only change one literal to get from one to the next. And we're just going to assume, imagine that if you drew a line down here, it would eventually come back around here. Same thing from here. Topologically, Karnaugh maps are actually toruses. So
Toruses?
you would be better off drawing this on a donut than a rectangle in theory. But
like it'd be like a cylinder, right?
But I can't afford to
Because
buy
cylinders
donuts
cannot
for this
go
class.
around like
but
that.
we had
Dude,
them last time.
But dude, I hate you guys and I didn't want to bring food, so I decided not to bring
Oh,
donuts.
man,
so
I'm
we're gonna use
sad.
rectangles instead of donuts.
we could have had a food example.
Yeah, and so then anyways,
Where's Lauren?
where's Lauren? I don't know. Well anyways, so
Lamenting her non-organizer role.
okay, so pretty much like you just fill in ones and zeros for like whatever you think for whatever so you put in a 1 whenever it should the expression that this is modeling. Remember a Boolean expression?
Yeah.
We're trying to construct a Boolean expression to represent this Boolean function.
Okay.
This tells us for this input and this input, like when these things are true, and this thing corresponds to the max term of P not Q,
I'm so
not R
You wanna
C,
eat that
right?
for this?
You just like concatenate these, right? It's this and this to get this
Oh,
column, right?
Taurus.
So
Oh, that's
this
what
is pretty
I
much saying that
said
this
Taurus
is
because
true.
it looks like a Taurus.
So pretty much what we could do is we could just say this or this or
Wait, hold
this
up.
or this or this.
Or this.
That would be DNF, right? That would be disjunctive normal form.
Yeah,
pretty
but,
much
like,
here
your
we
logic
just-
doesn't really check out like in actuality.
What do you mean my logic doesn't check out?
It's not
Check
R
out.
and Z and
Get check out.
What's not R and Z?
Everyone checks
wait, is
me out.
multiplication and or?
Multiplication is and.
Yeah.
Wait, so what doesn't check out?
I don't know.
Get check out branch.
Okay.
267 meter pistol. Give it this suck.
Okay, so. Alright, what
Oh,
was I
that
going
was
to talk about
funny.
next?
Okay, anybody going to ACL this weekend?
Oh, you want to go?
Dude, and so essentially, there's one thing that you can do to simplify this. Let's say I'm going to make this a block of all ones. So here's the thing. I can ignore, so I can say this and this and this and this and this, right?
Yep.
But the thing is, so I can do this, right? This is called an implicant. But the thing is, I can also say, wait a second, I can ignore Q. I have two of these options that are the same thing, so I can combine them. So that is an implicant, right? So essentially, I just eliminated Q. That makes it simpler, and it covers more solutions. Isn't that nice?
Yeah.
It's like
Less variable. So we say less variables, less literals in that min term.
Wait, so
The larger it is. And wait a second, I can ignore Z too. Oh my gosh. So now all this
What's
says
that?
is PR. That is this implicant, right?
Oh, that's probably how Candy Crush is made.
Yeah. And so the thing is, I can do this and this, and I can do this and this, or I could circle each of these things individually. These are all implicants, and it gets very crazy. So the thing is, we are only going to consider prime implicants, which means
Hey, what does an implicant mean?
an implicant is something that can be modeled by a min term, and it shows up as a square of ones.
I'm a noob, so.
Steve, Kevin.
Yes?
So it's a
How
min
come
term
he has
that's
a lot?
so it's like something that's like. So an implicant is just a block of all ones, right?
Wait, so how do you think about it?
No, school gives you a license. For multi.
Stop it being
Oh,
recorded.
Archie's octo until then.
An implicant is a block of all ones. We're never gonna. What time is it?
It's on
4:57.
450. Yeah.
Oh great!
Yeah,
I'm not even close to
lied.
finishing because of
You lied.
y'all.
You lied.
No, because
You
It's
can't
fine.
get distracted. You're teaching, right?
Yeah. Okay.
It's kind of cold.
So an implicant is a block of all ones, right?
It can be any
And
size.
it can be modeled like, it can be any size. Yes, it could be as small as this, or it could be like that, right? The only thing, and the thing is, and the thing is, I could even draw them like this. I could draw one, like let's say this was all ones, right? Right here. Yeah.
Wait, so
I could draw that, and that would work, because this would be, this would just be Z bar, and then P bar, right? That would be this.
I hate you.
So the thing is, they can all be represented as these expressions, right? Where you're like anding the literals together. It's not a min term because it doesn't contain all of the variables, ideally.
Are you using RS? Like, why isn't it like RS or RZ?
RM
Yeah,
dash
like
RF.
PQRS.
Okay.
It's not like PQRZ.
Good job. Okay, so a prime implicant is an implicant
No,
such
I'm
that
asking-
no other implicant
You lied.
contains. I
I'm asking-
chose the variable names.
Okay.
A prime implicant is an implicant such that no other implicant contains all the same ones. So for example, this tiny thing is not a prime implicant because this block contains all of it.
Oh.
But this block is, because you can't make a larger one that contains all of the ones in it.
So if you're making
So
a
the thing
larger
is-
block, would it be like
I'm gonna
4 blocks of 4, or would it be just like a? Would it like? Can it be like
the
a
thing
3
is,
by
I'm going
3?
to try and draw out for this diagram all of the prime implicants. So this would be one, this square, because none others contain all of them that these do. This would also be one, because there's no square that contains all of these, right? And then I can't draw this. This 3 long thing, that's not valid. It needs to be a power of 2 long. So it can be 2 long, or it can be 4 long, right?
So the next one would be 8 long.
Well,
What
the
happened?
thing is, it's like, I told you this maps onto a torus, right?
Uh-huh.
It gets a bit confusing when you go more than 4 variables. You don't actually want to use this grid thing.
Oh, so
What?
you can
What,
like.
Joseph?
What? Oh no, I
Wait,
was
so-
peering over Kevin's shoulder and breathing
Can I borrow that for a
over him very slowly, like every I'm
Yeah,
every
can I borrow that marker for a second? I want to ask.
You know, by the way,
So,
that's
if
he might
these-
use that.
Oh,
Ones,
Is he
right?
using this?
Yes.
This could be making like this could be like that.
Yeah, that could be. That is a prime implicant. David found,
Okay.
like David
How
showed
about
this thing.
37-minute mark?
This is also a prime implicant. Like I said, there are arrows drawn here. These
Okay.
sides are connected. These are not boundaries.
Oh, I see.
Not me.
So
Oh, so it's
there
like
are arrows
cylinder
between
shaped.
this.
It's a
I told you,
wraparound. It's
this
a
is
wraparound
torus.
map.
Think about this as a donut thing. So we're stretching and we're making these sides equal, right? And then we stretch and fold these sides over.
So
and when you
wouldn't
think
it
about it, that
sphere?
makes a donut shape.
No,
What?
because it doesn't
No,
go
that would be a
diagonally.
donut shape.
It can't go diagonally.
Donut.
Toruses are like actually like interesting.
Wait, oh Taurus. I kept on thinking you guys were saying Taurus because I think this looked like a Taurus. You know, you got the legs sticking out.
Okay, so
hey Eli, let's not let yourself get distracted.
Oh, sorry, man. I didn't. So.
Yeah.
And it doesn't go diagonally, right?
no, it has to be a horizontally aligned square like that. So an essential prime implicant is a prime implicant such that it's the only one to contain one of the ones. So like, let's say there's this one, and it's only contained by this prime implicant. That's actually the case, right? Joseph!
What? Oh.
And it's only
what it
contained
is.
by this prime implicant, right?
Yeah.
This is an essential prime implicant. We must use it in our solution. So the thing is, we're just going to pick prime implicants until we have a set that contains all of the ones, and then we choose the terms for this, right?
So can
So
you
we're
give
gonna,
us
we
an
have to
example
choose
of a
this.
non-prime
We have to
implicant?
choose this square because it's an essential prime implicant, right?
Mhm.
So that would be Q, Q R bar, right? And then we're going to say and then I'm going to choose this square and that square, right? So that would be PR, and this one is, let's see, it is P bar Z bar, right?
Yeah.
So that is our minimal expression, right?
Yeah.
Does it make sense how I got to this?
Yeah.
This is another way of manually getting through, like let's say we had a full adder, I could make a big chart of all the values, right? And that's only three variables, so it'd actually be even simpler than this one. And I could create a minimal expression for the full adder. It wouldn't make as much sense as the diagram we drew, but it would be completely optimal. And one of the things is, usually the column size is always larger than the row size.
Eli, so what would be a non-prime implicant then?
A non-prime implicant, like for example, this one.
Just a one by itself, so like.
This is not prime because there's a larger one that contains it.
Okay, so it's an implicant without like, so it's an
Or like-
implicant that's like part of the larger implicant.
It's an implicant that's wholly contained by another larger implicant. And it's only an implicant if it contains only ones. Because we don't want it to say true for something
That's not true.
that's not true, yeah.
Right, so if
And so
there was-
the other thing is, there is, so the greedy algorithm for like, the greedy algorithm for like making the smallest circuit, Joseph actually starts paying attention. Okay,
Because he needs this stuff.
is to start with only the largest ones. Like if there was one that contained this whole square, which there's not, or if there was one that contained like this boy or something, then we would definitely choose that thing first. Because it has the lowest number of literals in it. Actually, the bigger it gets, the less restrictive it is, which means like less literals in it. So it's simpler to write out. So we start with those and then we keep choosing more and more and more, right? Okay, there's also, let's say I don't care, these two inputs are impossible, right? So I don't actually care that it gives out a false or a true. I can put a D in here. This is like a wild card. It works as whatever. So if it's convenient to like let's say now I can do this, right? But I don't have to include this one. It doesn't matter whether the D's are included or not.
Wait, why
The zeros cannot be included, the ones must be included, the D's can be if you want.
Okay, so if there was like another column here, of all of these ones, then this would be like a an implicant too, right? And then these would all be non-prime if that was the one.
I guess, I'm not, it's confusing. Anyways,
Just go ahead and extend it, show.
Well, anyway, so let's just say we have some expression, right? That we want to create the optimal thing for. Like, let's say we have it in disjunctive normal form, right? So that's just a list of all of the ones, all of the tiny ones, the smallest implicants, like I showed you. So let's say it's PQR, or P not QR, or P not Q not R, or P not QR, something like this. You can already see how that's going to be reduced, right?
Holy crap! What?
Okay, so anyways, what I'm going to do is I'm going to number these min terms, right? I'm going to say this is number 1, 2, 3, 4, right? And I'm going to say, like, I'm going to figure out which of them are adjacent. And on the diagram, like I pointed out earlier, they differ only by one literal, right? If they're different by a row or a column. So that means that, like, if they were actually adjacent on the Karnaugh map, right? They will be one literal apart. So this might be PQ, right? This would be P not Q. This might be not PQ, right? These are all one apart, right? Make sense? Okay, and then, yeah. So on the Karnaugh map, they're literally adjacent, but here we're just gonna call them adjacent implicants, because like you can imagine that. So I'm gonna talk about Quine McCluskey, which is literally how you do, it's how you do Karnaugh Maps, but without actually drawing the rectangle. Drawing the rectangle, you're like, oh, I can just circle the biggest box, like, and you have an intuition for what is the biggest box. But here you have to actually solve it. Can you turn that off?
I turned it off. It was my Mac alert from earlier because I just connected to the internet.
Or did you look that up on YouTube? How to,
No,
like,
I
get
just
that?
got it. I
Okay.
have a, yeah. I did
Okay.
that. You want to see my Chrome history?
Okay, so
It's probably gonna be a bunch of furry logic.
or well, actually, you know what I'm gonna do? I'm gonna say or P, Q, not R, right? And that's gonna be my fifth one. Okay, so here, I'm just gonna reduce this, reduce common terms, right? For as many steps as possible. So I can just say, so I can say like here, like for, let's find out which of them are adjacent to 1, right? Which of them are adjacent to 1? Can anybody see?
Which one are adjacent to what?
Which min terms are adjacent to min term number 1? Which of them differ by only one literal?
Five.
So 2
5 is true.
2.
2 is true.
and
4.
4.
4 is correct. Okay, thank you. So what I'm going to do is I'm going to combine 1 and 2. That's going to be my new number 1. So how do I combine 1 and 2? I remove Q, right? Because it can be either true or false. It doesn't
Just
matter.
set to Q.
So PR, that's my new one. Or what is the combination of 1 and 4?
QR.
QR.
QR, that's 2. Or
PQ.
PQ, yeah. Now, I'm going to start with 2. What is adjacent to 2?
Well, 1 is, but you already have it.
Well, yeah,
So
after
2
that.
and 3.
All right, so then what gets produced from that?
So not QR.
That's true. And then what's next?
There's nothing else.
Wait, really?
Yes.
Okay, that makes sense.
You-
Now this
yeah, you
one,
need to
what's
write
adjacent to this?
You need to write 6.
What's
So
adjacent to
3,
this?
3 and 5 are adjacent. 3 and 4 are also
No,
adjacent.
3 and 5 are not adjacent. They're
Oh wait, never
exact-
mind.
um,
3 and 4 are adjacent.
Yes, that is true. So not PR, right?
Yeah.
And this one, is this adjacent to this? It is.
No, it's not.
Wait, oh no, it's not. Okay, so these are our new ones, right? It looks simpler. All of them only have 2 variables.
Do we do
Can
it
we
again?
do it again?
Can we?
Or wait, actually, I think.
Hold up. If we do
Were
it
you
again,
missing
don't we-
like
Or well, actually, this one.
Yeah, you're missing a
so
whole
actually,
bunch.
I need to I actually should have been keeping track of what these were created from. So this is 1, 2, right? This is 1, 4, and 1, 5, right?
Yes.
And then this is not
2,
QR.
3,
What was this
2,
created
3.
from?
2,
2, 3. Okay, and this is not PR.
Not PR, which is 3.
3. I think it's 4 and 5. No.
No, it's 3 and 4.
3 and 4.
Okay, so here's the thing. So we have them from 1, 2, 3, 4, 5. So we can actually completely ignore these. If any of them were not included in this list, we would have to get them back. Okay,
But don't we need to list out
so we
every
are
single
one step
possible one?
closer to getting prime implicants. So now, let's find which of these can this be combined with?
PR.
Which of these
PR
is it
and
adjacent
PQ.
with?
So
One.
PR and P. Wait, no.
PR and not PR, right?
Yes.
Okay, so that would be 1, 2, 3, and 4 all combined would just be R. Right?
Yes.
So there's no real need to go through this one, right? Because it's already contained
Well,
in
QR
this.
and not.
Dude, it's already
Oh,
contained
that's
in this. This accounts for 1, 2, 3, and 4.
Oh.
So
1
this
and
is
5.
just 1 and 4. So we can ignore this, right?
We can do 4
1 and 5,
1,
right?
4, 5.
So what is 1 and 5? What is that adjacent to?
1,
What is
4.
this adjacent to?
QR.
Nothing. It's not.
It's not adjacent to anything. All right, so we
Okay.
leave it.
Right.
Then these two are both contained in 1, 2, 3, 4, right?
Yeah.
So this is 1 and 5. So we have a list of prime implicants, right?
So like, does that?
This is a list of prime implicants, right?
Wait. So
Eli, so we can't do 1, 4, and 5?
no.
What?
We can't do 1, 4, and 1, 5?
Wait, 1, 4, and 1, 5. No, they differ by more than one literal. This has R, then you remove the R, and then you add a P,
Oh,
right?
okay.
It's supposed to be just like this or not that. Okay. So then, so we find the adjacent ones, right?
Oh, so the terms
So then now we have all of the, we keep combining adjacent ones and discarding discarding what we know not to be prime implicants, and now we have our prime implicants. So what we're going to do is we're going to make a chart, and we're going to say expression, these are all the different requirements that must be satisfied, right? This is a list of requirements. So we're going to make a chart, and we're going to say this is R, right? And this is PQ, right? And it's simple because this one we don't actually have to choose, because the thing is, like, look at this. So this, it accounts for 1, 2, 3, and 4, right? This one accounts for 1 and 5. So essentially, we would actually have to make a judgment decision. This is probably some kind of comp sci problem. So this is not actually something the algorithm addresses, but somehow you're supposed to choose the minimum number of rows such that every column has an X in it, right?
So that's 1.
So the thing is, we have to choose both of these to get an X in every column, right?
Yes.
We have to choose both R and PQ. So our answer is actually R and PQ.
Whoa, after
So
all
that it's Quine McCluskey.
That's R or PQ.
Yeah, that's R or PQ, right?
Wait, so is it R and PQ or
It's
R
R or PQ.
Okay.
Well, we have to choose both of these, right?
I see, yeah.
Because it's this PQ is true for 1 and 5, R is true for 1, 2, 3, and 4, and then none of these at any step in the process are true for anything that is not none of these are true at any step in the process for a 0. For
So,
something
like,
that is supposed to be 0. So we don't have to concern ourselves with that.
It's like that is congruent to what we had as the...
Yeah, so this is original ones. This is prime implicants. And you might note that what is PQ? What is a term we talked about for PQ?
5.
It is,
What?
yes, PQ is a 5. No.
Oh.
It's an essential prime implicant. It's the only one that satisfies 5. Right?
Oh.
So that's an essential prime implicant, right? And then I'm also just going to write up here, combine, because what we're doing is we're combining adjacents. And you know, at every step in the process, we have to have each number down here. And we just keep reducing, we keep combining and reducing until all of these are represented and there's no more adjacent ones. Yeah. So, that's how you do Quine McCluskey. This is like the rectangle method, but without the rectangles.
Damn.
All right, what time is it?
5.